Today we would like to learn how to calculate probabilities for normally distributed random variables. Here again is the formula for the normal distribution. F of x is equal to 1 divided by sigma square root of 2 pi e raised to the minus x minus mu squared power divided by 2 sigma squared. Okay? Looking at the formula for the normal distribution, it is not clear just how we are to solve the probability. If we do it, and we do it the way we have in the past, we simply put the data into the formula and do the math. To solve this problem, we can start by remembering that the area under a probability density function is the probability. This is what we're looking for. This tells me that the area between x1 and x2 is the probability I'm after. Mathematically, it would look something like this. Here is the normal distribution of x's. It looks like this. And here is our mean of the population x's. And here is x1, x2, and this is the probability we're looking for. Mathematically, we would say the probability that x is between x2 and x1 is equal to this area here. The mathematical tool I need to find the area under a curve is integral calculus. I would have to integrate the normal distribution formula between the points x1 and x2. Mathematically, it looks something like this. So there's the integral formula. I'm going to go from x1 to x2 dx. Okay? This is no fun, and believe me, it's very time-consuming. Now remember, there are an infinite number of normal distributions out there. Here is where we encounter genius, absolutely true genius. Someone, not clear who, more than a century ago pondered this formula and noticed that if the mean were 0, okay, and the standard deviation was 1, okay, that the formula completely collapses into a very simple idea. 1 over the square root of 2 pi, that's a constant. Pi is 3.14159. The value there is basically 1 over about 2.5. Okay? And we can then see that this collapses down to the minus square over 2. It's a simple formula to do that. And somebody has now calculated these for us. Okay? We can calculate the value for any x's that we want. Okay? These have been produced, and they are available in the text or everywhere online. They are presented in various ways. The table we will be working with is set up with the probabilities for 1/2 of the distribution, beginning with 0, the mean, and moving outward. The only problem is that even with this table, it would be ridiculous to consider that our data just happens to have a mean of 0 and a standard deviation of 1. The solution is to convert the distribution we have, this one here, with its mean and its standard deviation to the one that we now have here. This is called the standard normal distribution. This is the distribution that has a mean of 0 and a standard deviation of 1, and that is what is in the normal tables. Let's say we have one standard deviation. On the table, we go out as follows. This is the standard normal distribution. It, of course, looks like the other one. It has a mean of 0 and a standard deviation equal to 1. Now, let's say we would like to know the probability of going out 1 standard deviation. So this is going to be 1 here. Okay? Our area that we're looking for is this right here. We go to the standard normal table, and we go to the column marked 0. Okay? And we then go down to 1, and we read the value you find. And the value you'll find there is 3413, or this area here is 3413. The probability that x is between 1 and 0 is equal to 0.3413. Okay? This is what we have when you have at the top of the table. Fortunately, we have computed areas for any one normal distribution, and the areas for any distribution will have exactly the same probability. Okay? The essential point is the probability for one standard deviation on one normal distribution is the same on every normal distribution. If my data has a mean of 10 and a standard deviation of 5, then the probability from 10 to 15, one standard deviation, is the same as from 0 to 1. And we've already found that to be 0.3413. To compute probabilities areas, that is, for any normal distribution, we need only to convert the particular normal distribution to the standard normal distribution and look up the answer in the tables. The standardizing formula is equal to z equal x minus mu divided by sigma. Okay? What this allows us to do is to count the number of standard deviations. Note, we are using mu and sigma, which denotes population parameters. We are still dealing with probability, so we're always going to be looking at the population with known parameters and known distribution. Okay? It is also important to note that because the normal distribution is symmetrical, it does not matter if the z-score is positive or negative when calculating a probability. One standard deviation to the left is equal to one standard deviation to the right. This fact is why the standard normal tables do not provide areas for the left side of the distribution. And because of this symmetry, the x values are often written like this, where the formula for standardization is z equals x minus mu, the absolute value of that number. What the standardizing formula is really doing is computing the number of standard deviations x is from the mean of its own distribution. The standardizing formula and the concept of counting standard deviations from the mean is the secret of all that we will do in this statistics class. The reason is that the statistics boils down to variation, and the counting of standard deviations is a measure of variation. This formula, in many guises, will reappear over and over throughout this course.